Good morning everyone, thank you for joining me for this video. I am Mr. Ish. We've done many videos now when it comes to derivatives. We're looking back at natural logs here with slightly more detail and a slightly different perspective. If you remember with regards to the derivative of the natural log function, I presented this. Anytime you had a function derivative with respect to x and the function looked like this, you could go very comfortably to this as being your derivative of this type of a function. And I showed you two reasons why. One was if you did a substitution of u was equal to a to the x, like a chain rule substitution, this was my u, then f of u would have been ln u. You would do a chain rule and you do ln u and you do du or dx, ax. You would individually do the derivatives of these two components. Anytime you saw something like this, it was equal to 1 over u. Anytime you saw something like this, in terms of the derivative of this type of a polynomial character, you would just end up with the a. You would end up with a over u, and if you resubstituted for u, which was ax, you could come back to 1 over x right over here, which very well mirrors that. The other way you could actually look at this entire procedure, this was way number one. Way number two was using the properties of logarithms for right here. Anytime you have a product of logs, the impact of a single natural log, the product can be separated in terms of a plus and addition sign. You would have natural log a plus natural log x, and you'd be looking at the derivative of this new polynomial. The derivative of a constant here would always be a 0, but the derivative based on the template we know would be a 1 over x for natural log x, and you would again end up with 1 over x over here. But I want to show you how this is truly derived, because all I'm showing you here is how something which looks like this becomes 1 over x. I'm not showing you why it becomes that. I'm just showing you two different ways of how you can view that template. I want to show you the derivation of this actual 1 over x for something which looks like this. Then we can proceed with the remainder of this video. So to derive something which looks like this, natural log ax, we know it becomes 1 over x. To come to the actual derivation of this requires us to put our thinking caps on and think back historically to some of the earlier videos, such as the properties of logs, the video I've presented on that. And you can come up with these various items that we will remember from that past video, one of which is this. Anytime we see something which looks like log base e, it's synonymous with saying natural log, right? Log base e is synonymous with natural log. And another thing is, anytime we see something which looks like this, log ax equals y, it can be rewritten in this exponential form where a to the y is equal to x. Think about these two aspects that I talked about. This right here will exactly lean us towards this derivation process. Now look over here at this log ax equals y. Think of it as in this form, log e x is equal to y. You transform this into this format right here. What do you get? You get e to the y is equal to x. A technique that perhaps is not 100% familiar to us because we have not addressed it fully or in a comprehensive manner is a technique of implicit differentiation. Implicit differentiation is where you do not have an equation which is clearly expressed in terms of one variable, and you are doing the derivative of this. Right here, if you ever see an equation which looks like y is equal to and something, this is explicitly expressed in terms of y, because you're clearly saying the equation y is equal to something. But if you have something which looks like this, it's not explicitly expressed in terms of y, because you're not saying one variable in terms of the other. You're equally expressing both variables in that equation form. And when you do the derivative of this, you're doing implicit differentiation. When you're doing the derivative of an explicitly expressed expression, you're doing explicit differentiation. But to understand the derivation of this, you have to think about implicit differentiation. You take this equation right here and you implicitly derive it. And if we haven't talked about it yet, it's fine, because we will very likely talk about it in a very comprehensive manner and you will enjoy that video. Look over here, you have to do implicit differentiation, and if you don't know this technique, look at this part on its face value, because you will learn the technique very soon. You do the derivative of this entire equation in an implicit manner. So when you're doing the implicit differentiation from right over here, you have to bring in some of these other notations that we may not be familiar with, but we will soon be, as soon as we do that video. Derivative with respect to y, e to the y, dy over dx is equal to the derivative of this x. Now you're always solving an implicit differentiation for dy over dx. You're always doing that. What's the derivative of e to the y? It'll just be e to the y. E to the y dy over dx is equal to, what's the derivative of x here? It's just a 1. You solve for dy over dx because that's the the norm for when you're doing implicit differentiation, you're solving for this because this is represented by this, the derivative with respect to y. Anyhow, when you solve for dy over dx, you take e to the y on the other side, you get 1 over e to the y. Remember, we're still talking about the derivation of this. If you looked at our original equation, which was this, e to the y was equal to x. Think right here to this equation form right here. If e to the y is equal to x, e to the y anywhere in any derivation process can be substituted for x. So you're essentially saying 1 over x because you've substituted e to the y for what it exactly was, x. So you get this 1 over x over here, which mirrors the derivation we're seeing over here in terms of the derivative, and that's exactly how you derive this 1 over x from anything which looks like a to the x. The natural log a to the x will always be 1 over x. Let's look at it here in a slightly different form. Hypothetically, if supposedly we had a question which looked like e to the 2y is equal to x and we had to differentiate this, we would do the implicit differentiation over here, exactly similar to what I have talked about, and we would proceed with that. You do the derivative with respect to y and you'll do derivative with respect to x. The y playing in where the y variable is, the x playing in where the x variable is. That's for implicit differentiation. You do d over dy, e to the 2y, and then dy over dx is equal to derivative with respect to x of this x variable. You're always looking for solving for this item over here. What's the derivative of e to the 2y? You'll follow the scheme for exponential functions. It'll be 2e to the 2y dy over dx is equal to, derivative of x is just 1, dy over dx is equal to, what's 1 divided by all of this? You'll have 1 over 2e to the 2y. Well, what was e to the 2y equal to right over here? It was equal to x. So you can resubstitute x for where you see it. It'll be 1 over 2x. So now you're getting over here 1 over 2x. If you come back over here, e to the 2y is equal to x. E to the 2y is equal to x, and let's bring in the natural log properties over here. You'll do 2y ln e is equal to ln x. Ln e by a property of logarithm is always equal to 1. Y, you solve for it, take 2 on the other side, you get ln x over 2. So anytime you're seeing something like this, it's basically not equivalent to ln a to the ln ax is equal to, you're basically looking at a function which was ln a to the x divided by whatever that coefficient was here. In this case, you're getting a 2, which is why if you did the derivative of this, you'll get 1 over 2x. If you did the derivative of something like this, the a will still automatically be removed, but you'll end up with 1 over 2x. So these coefficients of these exponent y's will very well play into your final equation form. But when you have the coefficients attached to the x component and you're doing the natural log of that, that a component disappears. The coefficient for any of the y exponents do not disappear and they follow through into your denominator. These are the nuances that have to be kept in mind when you're doing natural logs, especially when you're looking at it from an implicit standpoint. When you're doing explicit differentiation, which is exactly this over here, the coefficient of the x will disappear, especially when it's equally affected by the natural log. And you've seen how that happens in the first two forms I showed you, which were not the derivative forms, but I showed you how the a disappeared. That's exactly how and why it disappears. In the explicit differentiation of natural logs, that a disappears. So let's take the very direct previous example and tweak it just a bit. If our equation was e to the 2y is now equal to 2x, and we're still trying to understand the effects of this over here, if we were to implicitly do the differentiation over here, and an interesting fact I haven't told you about implicit differentiation, which I probably should have earlier. If you've noticed, anytime I have a y variable, I'm doing this procedure. I have a d or dy, then the y variable, whatever it would be, and then dy over dx. If you remove the y variable, in essence, you're looking at d or dy and then dy over dx. You can cancel these dy's out and you still end up with d or dx, which represents the whole derivative process. We're going up towards that. But we'll be talking more about that in the implicit differentiation video. Anyhow, and the exact reasons of why we have to do it this way. But let's jump back right over here to this slightly modified version from the previous one, and we implicitly derive this. What will happen over here is this. We'll rewrite this in an implicit form, d or dy e to the 2y and then dy over dx. As I've said several times now, you're always solving for dy over dx. Then you're doing the derivative of this side also. You can take the coefficient out, d over dx, x. Do the derivative over here. The derivative of e to the 2y, as you know, from the template scheme of exponential function will be 2e to the 2y, and then you have the dy or dx attached to it, which you always solve for, is equal to derivative of x will just be here, a 2, the coefficient will remain. You're solving for dy or dx, and you take everything on the other side, you take 2 and you divide it by all of this right here, 2e to the 2y, the 2's cancel out, you get 1 over e to the 2y, and the original e to the 2y was equal to 2x, right, is equal to 1 over 2x. So you're seeing a similar effect play out in the previous example of that. So these are just the various ways of how you can look at derivatives of equation forms of this and how they somehow approximate or give you that type of a derivative for a natural log. That's how you're seeing it. But the very first derivative process where I showed you is exactly proving this, which was this one. When you do the implicit differentiation of e to the y is equal to x, you get that because you end up doing implicit differentiation. And I'm showing you very quickly over here, what you get is e to the y dy over dx. Remember down in the process we ended up having 1 over here, and then we solved for dy over dx, which was equal to 1 over e to the y. 1 over e to the y was resubstituted for 1 over x. This right here is basically the main thing you want to focus on in terms of all of this with regards to that. I will digress here a little bit just for the sake of digressing, because I'm going to introduce you to some new property over here. Then we'll get directly into further derivations and into the subject matter of this natural log derivative video. Look over here. If you have e to the x, which is an exponential function, you have b to the x, which is a power function, which in essence is also an exponential function. These are both exponential functions in their own sense of the word. You can relate one with the other, and you can actually say this right here is very well equivalent to that. And the reason why I'm saying that, because you can sometimes see equations with this and somehow you have to convert this into this form so you can do the actual operations. And why am I bringing you this up right now? Because it'll come in handy down the road when we look at some questions which involve this. If you supposedly you think back to the laws of exponents, you have a to the m multiplied by a to the n. You know by properties of laws of exponents the bases are the same. You add. You simply add them. But if supposedly your question was a to the m times, let's say b to the n, you don't have equal bases, so you cannot do this conversion using the law of exponents. You cannot marry these items under the same base because they're no longer under the same base. When I'm telling you over here that this in essence is the same base as this, if you think about a property of log, which I have not showed you but I will show you right now. And the property of log involves you to think of this from an out-of-the-box sense. Think of this as y is equal to b to the x. You have some function f of x which is synonymous as y is equal to b to the x. And now we're looking only here at this proportion y is equal to b to the power of x. I'm going to show you how b to the power of x is similar to e to the x in terms of having the same base. You have to bring in the property of natural log and get rid of this exponent and make it a coefficient, and you can do that very easily by x, l, and b. Now all you have to do is solve for y, and you know anytime you take natural log on the other side, you bring in the e function. Anytime you take the e function, the exponential base function on the other side, you bring the natural log. You know how to do that from the video on where we learned how to solve equations of exponential functions and equations of logs. So you take one on the other side, it becomes the other function. Remember, e and natural log are interconvertible based on how they go across on an equal sign. That's exactly what I'm saying over here. If you take the natural log on the other side, the natural log converts into the e function, the natural logarithmic base function. What do you end up getting? You get e to the x, l, and b. You see how somehow we've converted b base to the e base. See, we've converted b base to the e base, and now I've shown you that natural log e is very well seen in this by using a property of a log. Why is this relevant? Because now if I were to tell you to multiply them, you could e to the x times b to the x. If you ever had to bring these up using this type of property, you can, because b to the x is same thing as e to the x, l, and b, like I've just shown you. Using the properties of natural logs and manipulating using algebra, b to the x is equal to e to the x, l, and b. Now you can bring them together. The bases are the same. You add the exponents, x plus x, l, and b. You can further simplify this with a commonality here, x times 1 plus natural log b. Here I've shown you this is equal to that. That's just algebra over here, but I've shown you this. This right over here is the same thing as b to the x. So always keep these types of nuances in mind because they can help simplify those types of derivative or even integral questions that you'll see later on, especially which involve the power function over here. The power function, or you can call it the exponential function of a non-exponential base. So, and you do the relationship by this form over here, where you solve for y by taking the natural log on the other side and you bring in the natural exponential base. The natural exponential base takes the form of the b base you have over here. So all of this is in mind. I won't digress any further. We'll get into further derivations of some useful function, and then we'll get directly into the topic of this natural log derivatives. So before I actually discuss some examples, derivatives of natural logs, I want to talk about the power rule. Do not confuse the power rule for the power function, which is what I was talking about in my last video, this being the power function. I'm talking about the power rule, and you know I've talked about the power rule. If not explicitly, I devoted a whole video to it. When you think about the video, I talked about the polynomial derivatives, anything which looked like this, and you were using the power rule all along, even though I probably did not say so, and the scheme for that was BA x b minus 1. The only reason why I'm bringing this up over here is because the derivation of this power rule requires natural logs. If supposedly you have a function which looks like f of x is equal to, let's say, x to the power of n, when you rewrite this as y is equal to x to the power of n, because f of x is y, and you bring the n over here using the properties of logs, you get natural log y is equal to n natural log x. Now if you use again the technique of implicit differentiation, which is so commonly involved, you do the differentiation of all of this, look what happens. Derivative dy ln y and then dy with respect to dx is equal to n is basically a coefficient. You can push it aside, followed by the derivative of your x variable. Now look over here, you know the derivatives of natural logs are always 1 over that variable. You get a 1 over y dy over dx, and you're always solving for dy over dx is equal to n. Natural log x derivative is 1 over x. Look what happens when you take y on the other side, because you're still solving for this over here. Dy over dx is equal to n times y over x. And you know what originally y was? Y was expressed right here in this. Y was x to the power of n. You can write that again. Y substituted back for this x to the power of n over x. Now look over here, this is x to the power of 1. Use the law of exponents and bring this x up. When you're dividing exponents with the same base, essentially their exponents are minusing. You get n x to the power of n minus 1, and the symbol for dy over dx is really this, which is the derivative, and you're getting this as your final derived equation, which mirrors exactly what you see here, the power rule. So this is how the power rule is derived, and again the derivation of the power rule is depending very much so on natural logs and the derivatives of natural logs, so it made sense to bring it up over here. But let's look at some actual examples. I've shown you the derivation of the derivative of natural log x, which is just 1 over x. Now I've shown you the derivative scheme or the proof for the power rule. Let's get to the substance of this video now. So there are a number of questions that I want to go through over here for the natural logs, but very quickly as a rehash, if you just look again at a quick example of a power function, if you have a power function which looks like this, 5 to the power of minus 1 over x, you know this right here is a power function, and we know the derivative of power functions are easy. B to the x derivative is always equal to b to the x ln b. If I want to find the derivative of this, as you remember from the previous video, I always said chain rule, when in doubt, is the way you use. So I will use the chain rule over here. If u is equal to minus 1 over x, then function with regards to that u is 5 to the power of u. You can never be wrong with using the chain rule. Now you just do the chain rule over here. Derivative of du, and you know I'm just doing a quick example before we get into natural log. You get 5 to the power of u, and then du dx you get minus 1 over x, which is the same thing as what? You can write this as minus x to the power of minus 1. Minus x to the power of minus 1. So let's do that, because it'll help us with the differentiation of this. Minus x to the power of minus 1. You know the derivative of 5 to the power of u will follow this. You'll have 5u ln 5 multiplied by the derivative of this, minus 1 will multiply with this and make it a positive, and this minus 1 will be reduced. It'll be reduced by 1 to a minus 2. Look over here what you get. You get 5u ln 5 over x squared. You just have to substitute back for u with this item over here. Your final answer will be 5 to the power of minus 1 over x. You can write ln 5 first if you want, it don't matter, and x squared. And this right here is your final answer for this derivative. And we are done with this quick review of this power function. Do not confuse a power function for the power rule. This derivative of a polynomial involves a power rule, but I'm talking about here a power function derivative. Remember, all of these examples I'm showing you so far are explicit differentiation. Why are they explicit differentiation? Because look at them. The format is f of x is equal to or y is equal to, and you are explicitly given a function in terms of already solved for y. That's why it's explicitly differentiation, the process we're doing, because I'm explicitly giving you a function over here. Y is equal to, that's explicit. Now remember this, the derivative of anything which looks like this is 1 over x. When in doubt, use a chain rule. When you have a composite function, you should always use a chain rule. Here we have a composite function. Let u is equal to ln x, f of u is equal to sine u, and you always have to remember the previous derivatives you've learned, because here's a trigonometric. D over du sine u, and du over dx ln x, easy. Sine u derivative is a cosine u. Derivative of natural log x is a 1 over x, and when you marry these things up you get cosine u over x, but when you resubstitute back for the u over here you get cosine natural log x over x. The only reason why I'm spending a whole video on natural logs is because they're that important. But here's your final answer. Now when you look at this question over here, you have a product of two functions. You have a f function and a g function. You have to be using the product rule over here. But look over here, you have something which looks very much like this. Should you waste the time by making an extra substitution and doing a chain rule over here in addition to the product rule? You could, but you don't have to. If you look at this natural log 5x, you should know it should automatically give you 1 over x, so don't waste time with the chain rule. You don't waste time doing u is equal to 5x. Therefore f of u is equal to ln u, and then you do d over du, and you do ln u, and then du over dx. You do 5x, because all of this will still give you your 1 over x. You'll still get that 1 over x. We'll go directly here to the product rule, but we'll go directly to the derivative of this being 1 over x. And now watch, we have to use a product rule. Natural log 5x times the derivative of sine x plus sine x, your f function, times the derivative of your g function. This is a part where some people may want to put the chain rule because they had a doubt in their mind, which is fine. You couldn't go wrong with it. You go natural log 5x, and derivative of sine x is cosine x, plus sine x times the derivative of this, I'm just telling you, is a 1 over x, because the 5's would have cancelled out. Your final answer will be cosine x, I'm just writing the cosine x first, then natural log 5x plus sine x over x. There's no need to make a common denominator and bring an x over here. You don't need to, but this right here is your final answer. There's no need for you to go in through this route, because you would have ended up with this route anyways. Otherwise you'd be bringing the chain rule over here and just adding an extra step. But that's fine. If you want to do that, you can, because I already have said when in doubt, use a chain rule. Now this question over here will prove to be interesting, because I am seeing a composite function over here in regards to that natural log. But within this composite function, we might have a product rule play in. But let's see how it goes. We have to start initially with a substitution, because e to the minus x plus x e to the minus x is our substitution for u. Then function with regards to that u will be just ln u, because ln u, right? Now let's do the chain rule. D du, derivative with regards to du, ln u, and then du or dx, all of this. E to the minus x plus x e to the minus x, and here you know you have to be wary of the derivative of these exponential functions. So let's go to the next step. Derivative with regards to ln u multiplied. Now look over here what I'm doing. I'm eliminating this du or dx, because now I have a polynomial expression over here. Now I have to just bring the separate derivatives of these. E to the minus x, e to the minus x, derivative of this. Now look what happens. I have to bring the product rule over here, because I have a product of two functions. I'll do f times g plus g times derivative of f. E to the minus x plus d over dx. Remember, this is the product rule template, plus x times derivative with regards to that e minus x. g times the derivative of x. Here I have a plus, I don't know why I have a plus over here. G function times the derivative of x plus f function times the derivative of the g function. Here's my plus coming down here. Here's the derivative of this. This whole thing right here is a derivative of this right over here. The derivative of all of that is this expression over here. Now, let's start doing our differentiation. Natural log u becomes 1 over u. E to the minus x is just minus e to the minus x. Remember this rule here. The derivative of anything which looks like let me rewrite this. Anything which looks like e to the ax, when you do the derivative of this, becomes ae to the ax. Same thing if you even have a minus involved. The minus acts as a coefficient. Here you have a minus 1 coefficient. So the derivative of this is that. Plus e to the minus x times derivative of x, which is just a 1, plus x times the derivative of that is minus x e to the minus x. That's what you're getting. Now look over here, commonalities or things you can cancel out. This cancels out. You have a minus e to the minus x plus e to the minus x. These cancel out. You essentially have this over that. Look, minus x e to the minus x divided by u, which is e to the minus x plus x e to the minus x. Let's isolate e to the minus x from the top. You can write minus x times e to the minus x. Let's isolate e to the minus x on the bottom. You have e to the minus x over 1 plus x. Now look over here. You see e to the minus x, e to the minus x, everything is in a multiplying format. You can just cancel these out. You essentially get left with minus x over 1 plus x. And this right here represents your final answer. Not a difficult question, but more of an involved question. It was involved because of the matter of this chain rule, and within the chain rule you had to do a derivative of a polynomial type expression within which you had a product rule kicking in. But that's fine. When you take it through in a logical manner, you get your final answer and then you're done. This right here is your final answer. This is next to your final answer. This right here is not a good enough answer because it could have been simplified further. Now this question over here will prove to be an interesting question because you have a composite function here and you have a product rule kicking in over here. You could think of this as a double composite because you have a composite within a composite, but let's play this out. Our initial substitution and our initial approach to this question should be you're viewing this as ln squared and then 2x. So that helps you with your initial substitution where u is equal to natural log 2x. Therefore, function with regards to that u is u squared, right? But you have a product rule kicking in over here. So let's play this out. Here's my g function, here's my f function. The g function ln 2x squared multiplied by the derivative of x squared plus x squared, which is your f function, now multiplied by the derivative of this, for which we bring in the substitution d over du, u squared, and then du over dx ln 2x. Now you're probably thinking, here's another composite function. Let's do a v substitution where v is equal to 2x and then function with regards to v is equal to ln v, and then we'll add another kink. You could do that if you're doubtful, but you can also just look at the confidence you have in this rule and you know this is equal to just 1 over x. Don't bring in another kink. Be confident in this and just view this as 1 over x, as the derivative of this is 1 over x, and that's what I'm going to do. And I'll take this now to the next step. The derivative of x squared is a 2x plus x squared times derivative of u squared is 2u times the derivative of this is just going to be 1 over x. This x and this x squared you can cancel out over here. But let's worry about all of that later on. I'm going to write the 2x first because now I'm looking over here. Natural log 2x squared. Now look, this x can cancel out with this square and we can make it x to the 1. We can do that. But for the purposes of presentation, let me do that. We have x times u, you have a 2x times u, which is natural log 2x. Now look over here. There might be a common term. There is a common term. If you look as natural log 2x squared and natural log 2x, this has a natural log 2x, this has a natural log 2x. You have a 2x here and a 2x over here. So you have quite a bit of a common terms. Your common term will be 2x natural log 2x, which is all of this, which goes in this natural log 2x times plus 1. And this right here will be your final answer. Your final answer. And you would be satisfied and I would be satisfied with this answer. So let's look at this question. You have the natural log of entire this composite aspect, and you know you have a composite function over here, so you have to employ the chain rule, which requires a substitution. This entire aspect over here represents your substitution, x plus square root of 1 plus x squared. Therefore your function with regards to that u is natural log u, and you bring in the chain rule over here, d over du ln u, and then du over dx, all of this, x plus square root of 1 plus x squared. Now look over here, you can do the derivative of natural log u, you can get 1 over u, and then you have to separate this, because now we have to do the separate derivatives of this polynomial like expression we got going on over here, d over dx, x plus, now we have another substitution because this is composite. If v is equal to 1 plus x squared, then the function with regards to v must be equal to root v. See, root v. Okay, derivative of x plus, now we have to bring in the second kink into it, dv root v, and then dv over dx is equal to 1 plus x squared. Now let's see what happens over here. We have 1 over u, derivative of x is just a 1, derivative of root v is a 1 over 2 root v, and the derivative of 1 plus x squared is just a 2x. Now look over here, the 2's can cancel out. You can end up here with a 1 over u times 1 plus x over root v, x over root v. In this next step over here, I'll just write it out in this substituted format and see what we get. 1 over x plus square root of 1 plus x squared, where I am resubstituting back for u's and the v's, multiplied by 1 plus x over root v, which is square root of 1 plus x squared. This right here represents an answer, perhaps not a final answer because you still have to do the algebra part and come up with a very final simplified answer. For the purposes of this video I won't do that, but this part over here takes you towards the right track towards arriving at that final answer. But for this question over here, I'm going to end right over here. So this is not a difficult question. Imagine this right here, a rational function is your function, f of x is equal to this. And the question is actually find f prime of 1. What does that mean? It's basically telling you find, using the derivative of this, what the value of the slope is at point 1. And they're giving you your x value. All you have to do is first find the derivative of this rational function. Then using that derivative factor you have, you put in the 1 value, your f of x value, and you calculate the slope or the instantaneous rate of change. So you have to use a quotient rule over here. And so we're not just doing the derivative only, we're just taking this one step further. You have to use a quotient rule over here and do the final application. Look over here, you have to use a quotient rule. Here's my f function, here's my g function. The g function multiplied by the derivative of the f function, which is natural log x, minus the f function multiplied by the derivative of the g function, right, all over the g function squared. I probably need a new marker. Anyhow, 1 plus x squared multiplied by the derivative of natural log x, which is 1 over x, minus natural log x multiplied by the derivative of this 2x, all over 1 plus x squared. Now you don't have to be all crazy over here and actually try to finalize all of this. You don't have to, because all you have to do is plug 1 wherever you see the x's and bring in your calculator. And let's do that. Let's bring the calculator over here and do it. Actually, we may not even have to bring in the calculator. We're dealing with a 1. Everything will be easy over here. 1 plus 1 squared is a 2. 1 divided by 1 is a 1, multiplied by that 1, minus natural log of a 1 is always a 0. Everything here is zeros out. Divided by 1 plus 1 square is a 2. Square of that is a 4. I'm getting a 2 over 4, which is giving me a 1 over 2. That's my instantaneous rate of change, or the slope of the tangent line at point 1 will be 1 over 2, and you will be done with this question. So we didn't even need a calculator. And this question right here, answer over here is going to be right. Again, instantaneous rate of change, the slope of the tangent line, from which you could get the equation of the tangent line if you had the y coordinate. You would need the x comma y coordinate and you can get the equation. Let's look at one more question and we'll seal the deal with that question for this video. So we have a relatively different type of question over here with regards to the types I present. We have to use a derivative over here, derivative process of this natural log function to find the equation of the tangent line at point 1 comma 1. So you have everything you'll need. Once you get the derivative, you'll get your slope, you'll have your 2 points, and you have to do the equation of the tangent line, and you will use y is equal to mx plus b. But first we have to find the derivative. And before we do that, we have to recognize this is a composite function and we'll use a chain rule. If u is equal to x times e to the x square, because our function is natural log parentheses x e to the x square, then f of u must be equal to natural log u, and you do the chain rule. Derivative with respect to u, ln u, and du dx. Basically the chain rule is most commonly employed. You have x e to the x square. Now over here you have a product rule and a chain rule kicking in. But let's get to it when we get to it. Look for derivative with respect to u, ln u, and we're going to do the chain rule right here. Here's my f function, here's my g function. The g function, I'm sorry, we're going to do the product rule. If I said the chain rule, I was wrong. We're doing the product rule over here now. We did the chain rule initially, now we get the product rule, but the product rule will probably have another chain rule come into place because this e to the x squared is a composite function. Anyhow, the g function multiplied by the derivative of the f function. There are a lot of tongue twisters in these type of questions. When you're verbally saying them, you can misstate your words. Plus x, the f function, multiplied by the derivative of the g function. Now, let's cope with this. Let v equal x squared, therefore f of v must be equal to e to the v. And let's make the substitution right here. So derivative with respect to v, we have e to the v, and then dv with respect to its x variable, x squared. My x's are like monstrous sometimes. We have to solve all of this, and we have to do this. Natural log u derivative is 1 over u. E to the x squared, derivative of x is just 1. You have e to the x squared plus x. Derivative of e to the v is just e to the v. Derivative of x squared is 2x. Right? Let's do our substitutions. Resubstitute back. We'll get 1 over u, which is x e to the x squared multiplied by e to the x squared, a power on top of a power, plus x. Let's make this plus 2x squared, because x times 2x is a 2x squared, plus 2x squared e to the x squared. Now look over here, common terms, e to the x squared. We have that. Let's isolate this e to the x squared, e to the x squared. Let's start with isolating e to the x squared. E to the x squared, it goes into that 1 plus 2x squared times, and you get x e to the x squared. These e to the x squares cancel out, and you get 1 plus 2x squared over x. That's your derivative of this. 1 plus 2x squared over x. Now look over here, we've determined the derivative, but this derivative is just a factor because you have to plug 1 in here. You see the x value over here, this x value must plug in over here. Look what you get. When you plug this x value, you're getting your slope. You'll do 1 plus 2. 1 plus 2 times 1 square is just a 1 plus 2 is a 3. 3 divided by 1 is a 3. My slope is a 3. Now look over here, y is equal to mx plus b. We have to create room over here to finish our equation for the tangent line. Let's erase these substitutions we have and then proceed right over here, because we've determined our slope of the tangent line, which represents our instantaneous rate of change at that specific point. And we can use this specific point and the slope to determine the behavior of this function at that. But our behavior over here will be nothing more than the development of this equation. And we have the slope y is equal to 3x plus b. We have x and y. 1 is equal to 3 plus b. b is equal to minus 2. Right? We have b is equal to minus 2. So now all you need to do nothing more than just put this b value over here and get your final equation. And it will be y is equal to 3x minus 2. And you will be done. So you have basically started with a function, you have determined the derivative because the derivative gave you a factor, and that factor represented the instantaneous rate of change. When you actually plugged in the x value, you got your slope, and that slope was combined with the xy coordinate set to determine the equation. The equation of this curve, this is going to be like a curve, and you'll have that specific point. I'm not drawing anything to scale. You could have like a curve over here, something which looks something like this, and you have 1 comma 1, and you have a tangent line right over here. The tangent line right over here grazing at that specific point right here, 1 comma 1. This is a hypothetical image over here, only just showing you how a tangent line would graze a curve. over here. But anyhow, that was the video which I wanted to present. Natural log derivatives, more explained, more elaborated for this video. I hope you enjoyed this video. Please stay tuned because I have many more on the way.